Okay, let's get started. I'd like to welcome everyone for joining us. My name is Jerry Fallon, and welcome to today's CNCF webinar, Platform Observability, Building the Foundation for 5G and Edge Automation. I'm Jerry Fallon, and I'll be moderating today's webinar. I would like to welcome today's presenters, Sunku Ranganath and Killian Muldoon. Just a few housekeeping items before we get started. During the webinar, you are not able to talk as an attendee. There is a Q&A box at the bottom of your screen. Please feel free to drop your questions in there and we'll get to as many as we can at the end. This is an official webinar of the CNCF and as such is subject to the CNCF Code of Conduct. Please do not add anything to the chat or questions that would be in violation of the Code of Conduct. Please be respectful of your fellow participants and presenters. Please also note that today's recording and slides will be posted later today to the CNCF webinar page at cncf.io/webinars. With that, I'll kick it off to Sunku and Killian for today's presentation.
All right, thanks, Jerry. Hi, everyone. Morning, afternoon, wherever you are. My name is Sunku Ranganath, and I'm one of the tech leads in Network Platform Automation team. And we have Killian.
Yeah, my name is Killian Muldoon. I'm a software engineer with Intel's Network Platform Group. Mostly work with kind of preparing the underlying infrastructure for cloud-native packet processing workloads. And right now, see for this presentation, kind of focused on improving observability for those applications in kind of through the Kubernetes world.
Great, so here's the agenda for today's topic. So let's start off with providing some details into telemetry capabilities in Intel's network infrastructure platforms. We introduced the concept of telemetry reports and how it provides some actionable insights, and introduced the concept of closed loop automation. And later we have a whole bunch of demos. I promise I'll keep the theory short. And we have quite a few set of demos on closed loop actions with reports and automation topics, profiling, trends, prevention, etc. So a lot of action and excitement in store for you. All right. So when we look at network transformation, towards NFV and cloud-native deployments. As we address the challenges of some of our customers, we've identified 4 value vectors that we find are very much crucial. One is the ability to introduce new services and businesses rapidly, and second, high operational agility for opportunity to try and fail fast. And then resource efficiency with effective resource utilization, platform selection and scalability, and finally, improved end user experience. Now, across all these, one of the key attributes here in transformation towards cloud native is automation, which is what brings us to today's topic. So to achieve the real operational efficiency through increased automation, we require insights and information, meaning telemetry, about the hardware and software and services in the network. This includes, for example, your events, faults, utilization data about both the underlying hardware resources and the software and services running on top of these. A closed-loop automation solution then becomes crucial that combines essentially your telemetry data with analytics or machine learning, which in turn will help monitor and assess the network events such as faults, congestion, performance bottlenecks, etc. And finally, your orchestration layer would help perform the automated action to react to or correct these events. In order to enable these various levels of closed loops, Intel Platform Telemetry spans a vast number of functional domains. For example, your utilization insights, power consumption, faults, storage, performance, and more. So combining these granular information with similar data about how software and services are operating allows for a more holistic view of the network. So essentially, the observability of the platform and network insights are crucial for operational intelligence and automation. So let's look into some of the constructs of how platform telemetry is available and enables you towards the automation. So if you look at the stack from bottom up, right? So from your hardware platform, you can divide into compute, network, storage, memory, accelerators. So you have a set of collectors that you can run on the platforms, like inbound collectors, for example, CollectD, Telegraph, Prometheus, Node Exporter, etc. Almost all of these collectors have southbound plugins, which interface with the hardware to get the corresponding metrics and statistics. And you have set of northbound plugins, which interface with your monitoring and analytic systems. Of course, so you have your applications running on parallel, which these collectors can help you gather metrics from these applications. However, you feed in these various telemetry and stats into your monitoring and analytic systems. And on the other side, for example, one of the other consumers of these collectors is your resource orchestrators or your service orchestrators. And so a lot of these collectors, for example, CollectD have also a lot of write plugins where you can write to via HTTP or gRPC or UDP packets where you can send a lot of these stats out. In case, if you're a user of CollectD, there's a new release coming up, CollectD 6.0, with making it more cloud native and a lot of features inbound. So stay tuned for that. So now that, if you look at these collectors, if you zoom in a little bit more, right, so what kind of metrics or what kind of telemetry you get from the platform, as if you look across these domains, compute, network, storage, compute, for example, Intel's runs your technology, helps you get a lot of this reliability and resiliency type information, machine check errors, etc. Or you have Intel Resource Director technology, which gives you cache and memory bandwidth metrics, a bunch of power technologies that gives you a lot of power metrics on the platform. And if you look at network, your SROE, NIC counters, vSwitch counters, your storage metrics, a lot of these you can feed in with your collectors into your, across your hypervisor into your orchestrator, for example, Kubernetes. And you can do this both out of band with, for example, Redfish, or in band with the collectors like Prometheus and CollectD. So, one of the common questions we get is like, hey, you have so many of these technologies and metrics. How do I kind of visualize what's going on? Like, how can I understand these? To that end, we have a reference solution provided in the OPNFV Barometer project. So the project focuses on ensuring your platform metrics and events are accessible through open industry standard interfaces. And you have a easy way to demonstrate your importance of these various technologies and their corresponding telemetry, and how you can consume them and how you can act on them in real time. So you have a reference software called one-click install. So essentially it's an Ansible playbook where with one command you can deploy and install and CollectD, InfluxDB, and Grafana, and then you have easy visualization of a lot of these metrics that we are talking about across the hardware and across your containers. So now let me introduce you to the concept of telemetry reports in terms of analysis across the infrastructure platforms. Across this diagram, for example, if you look at telemetry analysis, how do you analyze and understand these? Telemetry report engine is what we're working on to help you provide that insight. For example, if you take any platform here that you have your container network functions or VNFs running here, right, easily per second, you can gather at least about 1,000 plus metrics just from the hardware on top of your application metrics. So from that perspective, so often one of the questions we get is, hey, I have tons of these metrics, hundreds of these metrics. Which one makes sense to me? Or what should I focus on? Or how do I understand these metrics? And that's where telemetry report engine can come into play, where it consumes these metrics and categorizes them, analyzes them into sections where consumes a subset and provides you reports into utilization reports, for example, where you can understand, okay, what's my hardware utilization? So, how are my software services and in my containers acting against these my utilization targets? Or your health reports, health of the platform, the health of your applications, or your congestion insights, right? So is there a noisy neighbor? Is there congestion by co-locating the workload? So a lot of these insights that you get that you can leverage, for example, on top of the existing analytic solutions. So this is not on top of, this is not apart from Prometheus or your commercial analytics solutions, you can leverage Prometheus and then have your telemetry report engine provide these insights. And then leveraging these insights, you can actually act on them. For example, you can feed into your SDN controller or root cause analysis or your NFV orchestrator or your Kubernetes engine so that you can understand this. If you have offline machine learning models and you can feed into them. And the idea is to easily understand and decipher the platform metrics and provide data that you can act on, right? So if I have a set of errors, like what do I do? If I have my health going bad, how do I understand what set of metrics should I look at? So here's a set of use cases so that you can understand how these bunch of metrics can come together. For example, platform health insights. You look at error reports and etc. And you can use this to drive corrective actions across your SDN controller and manual layers with failover or service reliability related actions. Or your utilization insights, right? So where you can use your management system or WIM, use these to detect platforms trending to resource exhaustion, or improve your workload placement decisions. And then you have your platform configuration checks. It can be used by management system or WIM to detect misconfigured platforms. Right? So there's so many capabilities on platform. How do I know, is this a secure platform? Is this a green platform? Right? So you can use your configuration checks. And congestion insights. Again, you can use this to plan your capacity across compute and your virtual switches to determine how overloaded your platform is. So there's a lot more information where this comes from. The sources here at the end. Here's a simple demo where you can look at your memory availability insights. Now, memory is one of those things you can easily understand what's going on. So if you look at here, so we look at this attribute called memory availability. What this means is, it's a length of time expressed as a percentage of the reporting period that your subsystem had 0 errors. So the fact that it's indicating 100 here means you had 0 errors. And on the right, we have memory error seconds. What it means is it's a length of time expressed as number of seconds of the reporting period had errors. So what we do in this demo is, as this memory error seconds keep refreshing every 5 seconds, is we'll introduce certain memory correction errors. And so to show you, give you an idea how the memory error seconds impact your memory availability. So we use this open source tool called MC Inject. So it's machine check error inject, and you inject a set of correctable errors onto your memory, and you're injecting a whole bunch of errors here. And immediately you start seeing, your memory error seconds has increased and your memory availability has gone low. So out of set of DIMMs that you have, we injected these errors into certain 2 out of 10 or a certain number of DIMMs, for example, and your availability of memory gone low. So it's back to 75. So you calculate or measure these across time. These generally memory availability is reported on a 24-hour period or 36-hour period, that period that you're configured. So for the demo purposes, we are looking at the scale of seconds and minutes. So for the last few minutes, right, so you have your memory availability reduced to 75. Now you don't have to worry about what metrics you're looking at, how to configure these, because the telemetry report engine is already consuming these metrics, corresponding metrics to provide you these appropriate value. And as your time lapses, your configure time lapses, you don't see any more errors happening. You can see your memory availability raising to 85 and then eventually to 100. So this gives you an idea in terms of your placement decisions or in terms of your operational flexibility, to give you an idea how to move around, how to efficiently automate a lot of this based on your telemetry. Let's see if we can move to the next slide. So next comes, so now you saw a little bit into the analysis part. Now, how would you automate all of this in terms of closed loop automation? So Intel architecture platform, it features quite a few set of telemetry, and also this essentially plays an important role in terms of your closed loop solution. So to enable this, from our side, we are ensuring that these features are detectable and can be provisioned and configured dynamically by your Vim or by Kubernetes. So they're currently capable of exposing metrics and stats to give an indication of performance. So you have a set of solutions, Intel Assist orchestration solutions to provide use cases such as scaling, healing, placement action to incorporate these platform features. Or you can, of course, we are also working with the commercial partners to integrate a lot of these in two-manner solutions. And on the other side, you have Intel-driven analytics solutions that use these platform-rich data, and so you can leverage these in your analytics solutions and open standard interfaces to orchestrators. And of course, you're also working with proprietary or commercial network monitoring and analytics solutions. So here's some use cases where we've been working on to show value that, on top of your service and software metrics, some of these hardware metrics help you with these use cases. So number one, if you look at service healing or platform reliability, right? So if you look monitoring these platform feature reliability counters can help you deploy workloads, for example, to the most reliable platforms, or help you proactively move workloads in planned maintenance windows to avoid potential outage. Or you can look at, hey, is my platform showing high load? Or, if you look at your reliability counters and load counters, you can look at when should I back off or scale out from a specific set of platforms? Or should I move my new workloads, new set of containers to platforms with sufficient capacity? And you can plan your horizontal scale out for overall resiliency scheme. So this is in terms of your service healing, reliability, and then if you look at your power management or energy optimization, there are quite a few technologies, for example, speed select technology, power management technologies that can help you, your applications. For example, if you monitor your applications that they're showing low load, you can look at scaling down your frequency on the core, on your CPU. The technology allows you to help scale the frequency up or down based on the amount of load that your applications, your platform has. Or if you look at your platform application metrics, it can help deploy new workloads to the nodes benefiting from higher frequency cores so that you can have the maximum performance for your high priority applications. Right, so having this ability to tune the frequency by your orchestrator can really help you, plan or scale your deployments and applications accordingly. And then there's application quality of service. If you look at some of the platform feature utilization insights and example your cache or memory bandwidth and CPU metrics, you can really configure your platform feature or your resource based on its priority so that none of the noisy neighbor applications are hurting your high priority workloads. Or you can move your applications between different priority groups as part of your network function rollout. So these are just some of the examples based on the telemetry that's available. And there are quite a few that are available that you can really build up your use cases. So next part, I'll stop sharing. I'll have Killian share to show you some of the parts, demos, and talk about the taking action part. So Killian, if you want to take over.
Yeah, so let me know once that's sharing.
Yeah, we can see your screen.
Okay, so yeah, thanks for that, Sunku. So what we've seen so far has been a look at some of the challenges with bringing these core network functions to a cloud-native world. And we've also looked at some of the capabilities that are unlocked when we move kind of closer and closer to a real cloud-native architecture for these packet processing workloads. So as we go towards this, platform and workload observability are going to underpin the movement, and closed-loop automation is going to expose a whole lot of power to cluster operators. So right now, I'm just going to jump into some of the nuts and bolts of the patterns that we're actually using to enable this automation. And I'm going to show a few ways that we can fully leverage platform data to automate actions inside a working Kubernetes cluster. So automated action, which is in the lower right of our quadrant here, it's one of the more intriguing, but it's also one of the more complex parts of the overall closed loop. In Kubernetes, we're constantly pulling in data from the platform and from the software and services that we're running. But as probably everybody in this call knows, it can be an absolute nightmare to analyze through the data to be able to get some signal and be able to separate it from the noise that's out there. So, but once you even get the correct metrics or events or whatever indicators you're using, you still need to find the right inflection point where you can take automated action. So in Kubernetes, there are some lifecycle events where these actions make a lot of sense. Kubernetes is flexible enough, it's extensible enough that we're actually able to use our insights to make orchestration decisions at these points. So today I'm going to show you two main tools and how we're using them. So one is the horizontal Pod Autoscaler, which is native to Kubernetes. And the second is an add-on that we've developed, which is the Telemetry Scheduler. So the horizontal Pod Autoscaler is a core component of Kubernetes. It's native. Most of the time it's used quite commonly to autoscale services on native CPU metrics. So this is just usually based on maybe a percentage of the CPU limit that you give your containers. And what it does is it scales up when you're using more CPU. So for packet processing workloads, this doesn't really work for a couple of technical reasons. But overall, it's just we're looking at more complex metrics when we're thinking about scaling. And there's also kind of technical problems with the way packet processing apps actually present CPU usage. So in this setup, the horizontal Pod Autoscaler is using metrics that are passed through from exporters. So we've seen collectd, we've seen the node exporter and Telegraph earlier. We store those in Prometheus and we pass them through to the Kubernetes custom metrics API. So that's a native API in Kubernetes, and we fulfill that using a piece of work called the Prometheus adapter that allows us to make Prometheus queries from inside the cluster related to Kubernetes objects. So once this plumbing is done, we can scale up and down based on split-second changes in metrics or other indicators in our cluster. So we found that automatic scaling for packet processors, it's a key tool because you're dealing a lot of the time with inconsistent, often time-based patterns. So they're somewhat predictable, but they're inconsistent, and you get a lot of scaling events where you get a lot of points where scaling events are useful. So day and night pattern is the easiest one, but you also get weekend, weekday patterns, and even sometimes we'll get time of year patterns, right? So you need extra capacity, simplest during the day, but at night you might want to scale down to consolidate into limited hardware and maybe run some other workloads on the extra hardware that you have. So right now, auto scaling is, in order to start, it's easy. The command is there, it's kubectl auto scale deployment, but those three dots at the end there hide a lot of complexity. And that's some of the stuff we're going to talk about today. On the other hand, then we have the Telemetry Scheduler. So this is a Kubernetes add-on. It allows you to bring kind of intelligent scheduling based on whatever telemetry you have, you can make accessible to it. So it consumes telemetry from the same telemetry endpoint, so through the custom metrics API. So this is important as tooling because it means once you instrument for auto scaling, you're also instrumented for scheduling. So once you have one up and running, it's much easier to add on more and use the same telemetry for both, or combine telemetry so that you can have scaling and scheduling acting in kind of concord with each other. So TAS, the Telemetry Scheduler, sits alongside the core Kubernetes scheduler. So all of the good stuff that brings, pod affinity, tails and tolerations, resource accounting, that's all still there. TAS just adds extra decision-making layers to the Kubernetes scheduling process. So this allows a lot of powerful decisions to be made. We can filter out nodes that don't meet our telemetry expectations. And we can also prioritize nodes based on whatever scoring you want based on whatever telemetry you have. So as we're just taking in raw numbers, this can be raw telemetry. So think memory usage or memory speed or the number of hits and misses on a last level cache. Or it could be some derived telemetry. So some combination of those numbers put together that references or represents kind of the real performance of some specific workload. So for normal workloads, scheduling is important, but the kind of packet processing workloads in the 5G core are going to find workload placement even more important. This is because they're long-running workloads and they have specific performance guarantees that they need to meet, and if they don't meet them, they're really not doing their job. This is going to be really important in bringing 5G to cloud native. So the scheduling process, because you're going to end up with the workload on a node for a longer period of time with stronger performance guarantees, it's really important. So there's a key part of the life cycle where you can bring intelligence in and have it help you to make proper decisions. So we're going to take a look at some automated actions here based on treating power as a contested resource. So this is thermal contention. This is when thermal or power contention, it's where one workload's just pure power usage actually is going to impact on the performance of other workloads. This can really become a serious issue in high performance packet processing workloads, because as soon as your CPU slows down, which is what happens in these contention situations, you can start to drop packets. This is a really, really bad problem when it happens. So here we're going to show a demo where we orchestrate around that problem. We use these automated actions. So we're using both the horizontal Pod Autoscaler to scale out workloads, and we're going to use telemetry scheduling to balance power usage across the cluster. And we're also going to prevent contention with the telemetry scheduling. So we're using collectD here as the base agent to collect the power metrics, and then collectD is going to expose those into Prometheus. So just a quick run through of what the demo is, and then I'll show a video of it actually in action on a cluster. So here we've got a similar setup to before. So we have telemetry scheduling, horizontal Pod Autoscaler. Those are all running in the Kubernetes control plane. And we have two nodes with collectD running both on Intel Xeons that are exposing these power metrics. So when we deploy our first pod, it just deploys on node 1. That's absolutely fine. Once it starts up though, it starts to use a huge amount of power on the system. As it starts to use more and more power, the horizontal Pod Autoscaler, its threshold gets passed, it sends a scaling signal. So this is a scaling sub-resource in Kubernetes, and it says we need another workload. So it scales up to 2. This second workload is scheduled. It's scheduled by telemetry scheduling. So it's actually, telemetry scheduling with this rule set is trying to balance power usage. So it sends the second workload to another node. The second workload, of course, because these are just power hungry applications, all they do is they just get on the node and they start sucking up power. So it's the second workload starts to use power as well, and we get another signal from the horizontal Pod Autoscaler. This time though, both of our nodes are in a red zone where they're using so much power that deploying another similar workload would actually cause contention. So we have our workload policy set up with telemetry scheduling where it knows that. It knows there is possible contention here, and we actually block scaling. So this third workload won't be scheduled unless a space opens up where it won't actually affect others. This is an ideal point where at another level of automation, you could actually add in a cluster autoscaling segment here. So now I'm just going to show a video of that up and running. So should be seeing it there. Sorry, it's the second demo. So here we are on the top left, we have power usage per node. On the bottom left, this is our list of deployed pods. On the top right, these are just our logs, our telemetry scheduling. So you can see we've already deployed our first power hungry application there. It's up and running on the cluster. It's going to take a few seconds to start up, and then it will start using power. This is just a CPU stressing application. In this case, it's stress NG running in a container. So on the top left graph there, the orange line is our threshold for scaling. So once we get above that line, we expect a horizontal Pod Autoscaler. You can see it's up there. The horizontal Pod Autoscaler will send out a scaling signal, and we'll see another workload be scheduled through the logs in the top right. There it goes, and it will start to appear in the bottom left as another pod. So we can see at the bottom left that it's actually been scheduled on node 2. That's telemetry scheduling, prioritizing nodes with lower power usage for subsequent deployments. Now, as we saw in the earlier model, what's going to happen is the second workload is going to start using power again. And this is going to cause another scaling signal to happen. So that's going to take a couple of seconds more. Once the second scaling event happens, we're probably going to have both of our nodes in the actual red zone, which is where we can't schedule any more to these nodes. So we see in the logs there, a little bit confusing in the logs, but all of our nodes have been filtered out. There has been no node selected for the third workload. And on the bottom left, our third workload has appeared, but it's going to be stuck in pending phase. And like I said earlier, this will be stuck in pending phase until one of our nodes actually has enough power headroom to take the third workload, or we could auto scale out to free up another machine. So there's a lot of different types of resource contention and congestion that can impact high performance packet processing workloads. Power consumption is one that maybe a lot of cluster operators don't think about all the time, but it does play an important role in the overall data center. And when it comes to 5G workloads, high throughput workloads, it's even more critical. So this is particularly true, like in the last example, where you could run multiple of these workloads that suck up a lot of power on the same physical server, and you don't want them contending for any sort of resource where you can avoid it. So that includes memory, it includes CPU, and at this level, it includes power. So here, TAS and the horizontal Pod Autoscaler have given us the tools to actually orchestrate around that contention to try and prevent it from happening. So when we get into the application realm, we actually get a bunch of application-specific metrics. So power is obviously based on the platform, but we can, 5G apps, there's a bunch of them that would form part of the 5G core and the 5G edge, similar to other network processing. There are specific application metrics that we can use to perform automated actions as well, right? And cluster operators, the people who design and manage these applications, will know specifically which of them are the best to use. So here we've got ongoing work with the user plane function. This is a core feature of 5G. It's part of the service-based architecture of 5G. This is where pretty much all your subscriber traffic is going to come in. And we're working on auto scaling based on the received packets here. So this is a measure of kind of subscriber intensity, not only how many subscribers, but also how much traffic they're using at any one time. So we're just honing in on that number of received packets, and we're going to auto scale them as those packets go up, and new traffic is going to be diverted or load balanced across to the newer workloads. So this is again based on thresholding. It's based on the horizontal Pod Autoscaler. So there's ways obviously to mix and match this application specific telemetry with some platform telemetry. So you can imagine here that we can auto scale based on maybe received packets in the application, but we could then schedule based on power usage. We could schedule based on available NIC bandwidth or other metrics like that. So up until now, we've mostly been focusing on scaling in reactive terms. So that's, if something happens, then do this, right? Now we want to move on to think about some of the more powerful opportunities that are there for platform observability. And that's it really in trying to make decisions proactively. So we try to bring smoother operation throughout a workload's lifecycle by actually acting before we have any performance impact, before we have some kind of operational need. So this can be really, really incredibly important in 5G workloads, where if you're losing packets, they're somebody else's packets, right? You might control the data center, but it's actually somebody else's traffic that belongs to some business, some web application belonging to somebody else, some end user who's having either slower network connection, noisier network connection on a video call, maybe a lot of drop packets, or maybe they just get cut off momentarily, right? So these are actually real impacts that happen. And if we can profile trends and prevent events from happening, that's actually a really powerful tool in our arsenal here. So here I'm going to talk about a host health indicator, which we use to track trends in various platform telemetry. So the memory error metric that Sunku showed us earlier, that was part of this, and it was put into an analytics solution to produce an overall score of host health. And this wasn't a score of how healthy the host is right now necessarily. This is about capturing the trends of where the host is going. So this involved a Kafka streaming analytics solution. So our analytics coming up off or our telemetry is raw telemetry coming up off the platform. It's going into a Kafka streaming solution. And in the demo, what we're going to do is we're going to, like Sunku showed earlier with the dashboard, we're going to directly just inject errors in to this demo. And we're going to see how telemetry scheduling in this case is able to react. So it's the same telemetry aware scheduler that we saw earlier with Power, but this time it's going to be working with this resiliency host health metric. So the first thing we're going to see here is a minor alert. So a minor alert is some sign that maybe there's something wrong and somebody needs to take a look at the platform, but a minor alert is something that could resolve itself. So in that case, while there is a minor alert, we basically want to stop scheduling critical workloads to that node. On the other hand, if we have a really bad trend in the way these errors are going, we'll throw a critical alert. And this critical alert basically means that we won't schedule. And also the workloads that we have on that node, we will start to proactively migrate them to a healthy node. So this is important because when we know that the node is going to fail anyway, we try to prevent our important workloads from being on top of it when it does fall over. So even though we might take some disruption, we're actually minimizing the disruption, maybe spreading it across time, which is important. So this is the setup of this demo. So again, we've got two nodes. We have a bunch more platform telemetry coming into Collect D and going into our stream analytics. So we've got Intel RDT, which are cache metrics, PMU, which is performance counters, IPMI, run sure technologies. Those are all going into our analytics, which is then through the same patterns we've seen before, going through Prometheus, the custom metrics API, and eventually into the telemetry scheduling component, which is where our intelligent decisions are really happening. So a yellow indicator will prevent scheduling, whereas and the workload will go on the healthy node, whereas the red indicator will actually cause direct migration. So we actually get the workload to be moved. This leverages the Kubernetes descheduler. So this is it's not a native part of Kubernetes, but it's a community project in Kubernetes. It sends these scheduling signals to specific workloads, and then the Kubernetes controllers manage rescheduling and redeploying a similar workload to the healthy node in accordance with the rules of TAS. So just going to show a video of that now. So here's another look at our setup. We have the streaming analytics solution, time to our scheduling running. We start here with 4 workflows, so there's 2 on each node, node A and node B. We hit a button here, which is going to trigger these memory errors, and we can see these errors pick up and they start turning our host that they get orange. And then when we deploy our new workloads, they'll actually be deployed to node B, which is showing green and healthy. So there we go, workload 5 and 6. So now after resetting our cluster back to its original state, this time instead of injecting minor errors, we're actually going to inject critical errors, really high levels of errors. We're seeing that the platform is changing towards being very unhealthy. In this case, the telemetry scheduler is going to actually pick up the indicator and it's going to decide to migrate. So you'll see these workloads disappear, and then very quickly they'll start to spin up again on node B. So we can see there is some disruption caused there, but this is about minimizing the amount of disruption that we cause when we're running into a critical health issue on a node where we're going to have issues anyway. If you have a situation like this, you would hope that you have some resiliency, some high availability built into your services, but this automation will help to maintain that availability through an event where a node is actually just going to go down. So there's near unlimited possibility in automating any process on the basis of not only what's going on the platform right now, but also where we see the platform going based on telemetry and other information. So this predictive analytics is really hard to do. It's really hard to get good answers out of it. But if we can actually come to some conclusions and some useful indicators, we can actually perform a lot of interesting automated actions. So this resiliency demo is just using node health as a way of seeing that the nodes are trending towards failure. And like we showed, we're preventing our essential packet processing workloads from failing while those nodes are failing. So machines do break, and telemetry scheduling is smart enough here with our policy and with our full streaming analytics solution to see that those failures are on the way or that there's a heightened risk of them and prevent workloads from being scheduled there. Or in the extreme case, as we showed, actually migrating workloads across to a healthier node to improve service health overall. So the network is edging closer and closer and closer to this cloud native reality, right? This is going to bring a lot of opportunities for automation and for scalability, but it's bringing real challenges in observability. So once we break down big workloads into smaller workloads, we get more communication, we get more diversity in the languages used, we get more diversity even in the number of teams that are actually creating these services, and you get inside organization and between organization overhead and communication between teams. So observability is going to be a big challenge, and solving the basic observability problems here from the platform level, from the application level, from software and services, it's going to streamline the management of cloud native network functions. So where the end goal of making these network functions cloud native is to get to something like end-to-end automated management of these services, reducing operation complexity and improving the resilience and overall performance of these workloads is key. And whether or not we reach that actual end goal, that sort of utopian ideal of a fully automated in-software network that only needs a few hardware engineers to understand what's going on underneath in the undercloud, that's going to depend a lot on how we actually manage observability and how we make observability bleed through the entire orchestration process. So between all of the raw telemetry, the analysis that we can do, and the automated actions that we showed earlier. So what we've shown here today, from the telemetry collection all the way through to automated action, this is just the basis of what we'll need to do to actually make these services orchestratable and then eventually actually orchestrate them. So there's a number of documents on this network builder site. So this link here, I think we'll post this in the chat later on, but this link is available in the slides which are on the CNCF website. These documents will go into detail on the closed loop architecture, the demos that we've shown here today, and you'll also, if you have any interest in any of these use cases or in any of the specific technologies discussed, you can reach out to either myself or Sunku. Our emails are listed there. So now I think myself and Sunku are available to take any questions you might have.
Thank you both for a great presentation. Here's one question we have here. Can we get flame graphs from these telemetry insights?
Yeah, that's a good question. So this is very much work in progress as you're building the telemetry engine and then providing a reference set of telemetry reports. So we'll be hosting all of this soon, pretty soon in our website, so you can take a look.
Okay. Where can I get involved if I want to contribute to some of the projects that cover this work?
There are quite a few opportunities to get involved in that sense. I could talk to through the telemetry side of things, and Killian can mention about Kubernetes side of projects. So if you look at so contributing to the telemetry and metrics, you have Collectee, Telegraph, Prometheus, Null Exporter, and some of the communities we are contributing to. That's a really good place if you're from an open source standpoint that you can work with. And of course, there's a whole set of areas that we're working with the closed loop automation space. You have OpenAV closed loop automation working group that we run on a monthly basis. We discuss standards or some of these analytic solutions. So that's a really good place. And then of course, there's OpenAV Barometer project where you can get involved in terms of how to leverage these telemetry and metrics across your NFV or your edge deployments. So yeah, and it's very much wide open space that you can start getting involved in terms of observability and telemetry. And Killian, you might want to add more.
Yeah, so specifically what we showed here today, so the horizontal pod autoscaler is part of core Kubernetes. That can be obviously really intimidating for anybody to approach. But there is a SIG, which is SIG autoscaling, which manages that. There's the vertical pod autoscaler. Those all accept contributions and they love to hear use cases. From our own side, we have Telemetry scheduling, which is what made these scheduling decisions today. So this is also, it's open source. It's under an Intel repo, but it's community owned, so we accept any issues or PRs that you might have, any ideas for features. We'd love to see them. So that link is in the presentation there, but I will also paste it in the chat in a second. But yeah, so one of the great things about this observability world and the Kubernetes and cloud native is it's all wide open and open source. So there's lots of places to contribute, but yeah, I would recommend the autoscaling SIG and Telemetry scheduling for ideas related to automation. And like Sunku said, I think they're Collect-D, Telegraph, and Node Exporter all accept contributions on the telemetry side.
Yep, there's some more links, references at the end that you can take a look to get started.
Okay. In 5G high throughput environment, what are the relative comparisons in terms of power consumption comparing to 4G?
So I don't have any specific numbers on that. I guess the issues related to that are, it depends on the workload is the point. So I think 4G, there is no open 4G cloud native implementation that I know of, whereas 5G is kind of designed to be mapped onto cloud native models to start with. So I don't know is the answer to that question.
Are there any good links related to VNFs and its functionality?
Yeah, so I just pasted a link about Intel Network Builders page and some of the service assurance solutions. So this can give you some idea about some of the reference VNFs and container network functions that you can start looking at in terms of overall closed loop context or service assurance context. Of course, feel free to contact us and if you have more questions, we are happy to help.
Is it okay to elaborate a bit on the closed part?
Yeah, so let's see, we go back to slide 15. Yeah, so this is a very minimalistic diagram, just not to complicate things. But then, if you look at the closed loop automation aspect, right? There are multiple closed loop in order to give you an idea, right? So the closed loop within your hardware platform, you're looking at your metrics within milliseconds or seconds time frame and taking corresponding actions. So you need something across in your node. We're running your containers within the nodes to look at the metrics and analyze them, and then the corresponding your orchestrator container manager can help take those corresponding action. So that's one level of closed loop. This is within the platform, right? Your feature exposure, telemetry exposure, feature provisioning, and then you have an agent within the platform that can act on based on the data that's coming in. All right. So, and then if you look at a closed loop within your Kubernetes cluster, for example, you look at across your cluster deployment, 10 nodes or 20 nodes, whatever your deployment is, and try and feed all of these metrics into your time series database, for example, Prometheus or Influx, and then have your analytics agent can understand, okay, this is what my cluster service level objectives are, and this is what my service assurance constructs are, and am I meeting them? Do I have to worry about my power? Do I have to worry about my health? And then within the cluster, you can take that corresponding action, which Killian kind of alluded to some of the demos that's within your cluster closed loop. And then a closed loop across your services. For example, if you go across the NFEO layer and the Mano layer for reference solution, for reference designs like what ONAP provides you. You have something called DCAE, Data Collection Analytics Engine. So DCAE can look at across your multiple clusters, across your cities or multiple deployments, and then there you're looking at kind of like a big data scale. You're looking at these multiple observability data and then acting on that for multiple set of your clusters. So there are multiple set of, you can say, closed loops, and depending on the level of granularity that you're going for, it can start from the top or from the bottom up. And a lot of examples and demos we give you looking at Kubernetes cluster and below or within the hardware, and often overlooked because you're more focused on your software and services telemetry or service level objectives, meeting them. However, if you start going up from bottom up, then you can unlock a lot of these use cases that we were talking about. Yeah, hopefully that kind of provided the answer.
Excellent. What other companies are involved in some of the open source collector efforts you mentioned, like CollectD?
Yeah, CollectD, it's been there for a very long time, 10 plus years nearly, and there are quite a few folks involved. Community is very active. For example, we have maintainers from Red Hat, folks from Google. Google uses CollectD in their GCP platform, a Stackdriver solution. We have folks across the board, like a lot of contributors from various companies. If you look at the open source community, the new contributions, bug fixes, or issue requests, or pull requests. So a lot of these come from a wide variety of companies across telco domain, cloud domain, and a lot of folks from universities too that contribute to CollectD and utilize that. The biggest thing is having CollectD part of your Red Hat OpenStack platform kind of gives you an idea of the breadth of deployments across your telco deployments, like Red Hat OSP is a very popular product which leverages CollectD. And then, of course, you have Telegraph and Node Explorer. Just looking at their GitHub gives you breadth of folks that are leveraging these solutions.
Excellent, excellent. Do we have any other questions at all? In the presentation, it shows that TAS involves in collecting telemetry and for workload hungry pods are getting migrated to other nodes. So that migration is taken by scheduler. How TAS communicates with scheduler.
Yeah, so telemetry scheduling is a scheduler extender. So every time a scheduling decision is made, if it has a telemetry policy attached to a telemetry scheduling policy attached to it, then the scheduler actually will call out to it. So that's a HTTP call. And then the telemetry scheduler will return with its opinion. So in the migration example, what's actually happening there, it's not migration like live migration with a VM. What's happening there is we actually deschedule the workload fully once certain conditions are met. So we can wait until traffic has reached a low or take some mitigations. And then Kubernetes itself, when you have a deployment, it realizes the desired number of replicas is below the actual number of replicas, or is above it, sorry, and it will deploy a new workload. So that what we had as migration there is really descheduling and rescheduling.
Okay. Well, everyone, that's about all the time that we have for today. I wanted to thank our presenters for presenting today. As I said before, today's presentation and slides will both be available on the CNCF website later today with links that were referenced earlier. Everyone, thank you again for joining us. Have a wonderful day and have a wonderful long weekend if you have the chance to relax. Take care, everyone.
Thanks.